Hi. So now we're going to go a little deeper into the finite element modeling with the example that I started with, which was a straight rectangular rod. And now we're going to add some detail features and see how that affects our results. Here we are back in SolidWorks, and I'm just going to go and change this model a little bit. Go back to the model tool, and I'm going to add a hole. I'll just make an extruded cut on the on one face of my model. Whoops. And I think I'll put my extruded cut on this end. I'm just going to drill a hole. We'll make the hole, oh, let's see, it's a 10 millimeter bar. We'll make the hole 3 millimeters in diameter. And what we'll do is we'll dimension it so that it's in the middle. So we'll make that 5 millimeters. So now we have a single hole through the rod. And I'm going to cut through both. There. Pretty simple change. We've taken a drill and drilled a hole in this model. Now I'm going to save that. And we'll go back to our simple model. Now this is the model that has the roller constraints, which we found matched our PL over EA. Because now I've changed the physical model, I'm going to create a different mesh. And we found that a 2 millimeter mesh was a good one before. So I'm going to stick with that, and we'll redo the mesh. Now, first of all, looking at what the mesh tool has done, now you'll recall that in the discussion in a previous video about finite element method versus finite difference method, finite difference method fundamentally needs a very regular grid, very regular mesh to do the model. One of the strengths of finite element method is that each of the elements can be very weirdly shaped. And we can see that here. We haven't increased the number or the size of elements. What the software package has done is it's adapted those shapes around this hole feature that I've created. So everything else basically has stayed the same. The rest of the grid is the same. Those changes are localized in here. Now, you know from the previous video that the way that this tool is going to solve the deflections and the stresses is it's going to do a matrix inversion of a very big matrix. One of the powerful things in the solution method is that a lot of what we've changed in the model is very localized in whatever that matrix is. So it's a small subset of the matrix that represents these grid points, because each of these tetrahedrons is one of those weighting factor W's that I described in the previous video. So let's see how this goes. Run the model, and you can see that we have quite a different behavior here. Now, what's curious about this is we've got this necking down of the model. Let's look at the strain. We've got this necking down to the model on one side, but not so much on the other. And there's these features here. Those look a bit odd. Now, the other thing that's happened is that the hole that we drilled a circle has stretched. And that's rather strange. Now, if I look at the results advisor, has our as our deflection changed, recall that this was 9.52 previously. Well, now our deflection is 9.62. All we did was drill a hole, a very small hole in this, and the deflection has changed quite a bit. Now, admittedly, that's only changed by 0.1 microns, but it's a change. And depending on what we were doing with this part, that might or might not be significant. Certainly, in terms of what it means for our modeling, that change has been rather unusual. So what we've seen here is an interesting interesting effect. Now, just like before, I'm going to go back and modify this mesh. Now, we've worked with a 1 millimeter mesh previously at one point as the smallest one. And this will be a much longer solution time. And you can see that there's very fine number of grid points here. And now we have a solution. And if I look at the stress, you can see that we are seeing features in this model in the stress that look like they're fairly fine, because the mesh size that we created can represent those kinds of features. However, notice that there also may be an artifact of the grid size shown in this sort of star pattern. And we don't really know, without doing a detailed study of the mesh, whether or not we're creating effects in the solution because of the mesh that we used, or whether the mesh is simply accurately reflecting what would be happening in real life. That's the challenge with finite element analysis. We can make all these pretty pictures, but if we don't appreciate the limitations in them, and whether or not we're seeing the truth or we're just seeing an artifact of the way we've modeled it, that's what really is important. And that's where your skill as an engineer and as a modeler really come into play. So what I'd want to see you doing in the case like this is I'd like to see a variation of parameters and then comparing the results. So for instance, we could do a number of runs of this at different mesh sizes, and that would tell us how much of the size of the grid has an effect on the result. Likewise, we could try some other meshing schemes. So we could modify the grid points so that the mesh maybe is much finer around the place where something interesting is happening with the stress and the strain. Or we could use another type of mesh. Now, in SolidWorks, we don't have as much control over the elements as we do in ANSYS. In ANSYS, we can do a lot more to customize the grid points to make it more appropriate for the model. But we can still do some things here. So we've just looked at a simple example of adding a detail feature to a simulation and seeing how much of an effect it possibly could make. In fact, adding that one hole had as big an effect on our solution in terms of the total deflection as all of the previous discussion we had in the previous video about looking at the boundary value or boundary constraints that we were applying. So that detail of getting the accurate model is essential, and then knowing how to vary it to not only test your design, but also to test the accuracy of your simulation tool. So we'll talk a bit more about this in the next video.